There will be a lab associated with this, so make sure you watch this section before you get to it. I think it'll be up next week. Can't quite remember, but it's on the schedule. So, what is Le Chatelet's principle? Le Chatelet's principle says that when a system at equilibrium has a stress applied to it, it will shift in such a way to relieve the stress. So, how do you stress an equilibrium system? You change the concentrations of either reactants or the products. You can change the temperature, you can change the pressure. So those are the three main stresses, and we'll look at each of them individually. But for those of you who are visual, what we've done is if we're at equilibrium, think a teeter-totter. If you stress the system, you're going to push it down on one side, so you're going to have to shift to relieve the stress. So we'll shift to relieve. In this case, we can go this way to relieve the pressure. And it depends upon what the pressure is, and then we will reestablish the equilibrium. So, again, I think of a teeter-totter, and if you push it, it affects it. So, first thing we are going to look at is the change in concentration of the reactant. If you increase the concentration of the reactant, you're going to shift to the product side. If you decrease the concentration by removing some, you shift back to the reactant to replace it. The rule of thumb, if you add it, get rid of it. If you remove it, replace it. If you change the concentration of the product, if you increase the concentration, you're going to shift to the reactant side. If you decrease, you'll shift to the product side to replace it. Again, if you add it, get rid of it. If you remove it, replace it. And it's an equilibrium, which means you can't randomly pull in stuff just to dump in to reestablish. You can dump in to affect it, but then it has to establish within the reactant product. Now, the other trick is it only affects species involved in the equilibrium. So back when we did the equilibrium expressions, and we were able to drop them out because they were pure, guess what? Again, if they're pure, they will drop out so it doesn't affect it. And I'll show you as we go. So if we have our equilibrium here, this is As2O6. So diarsenic hexoxide plus carbon yields arsenic and 6 carbon monoxides. Okay, so we're going to add CO. So if we look at it, adding CO is a product. So we're going to increase the products, which means we've got to get rid of it. So we're going to shift to the reactant side to remove the product. Okay. So that was really easy. Now, if we look at it, the next one is we're going to remove some carbon. So that's a reactant, so we should shift to the product, right? No. There's no effect. Why? Because we're removing some of the carbon, and as long as we've got some solid present, then it drops out. Now, if you were to remove all of it, then you would have to replace it because you have to have some solid present. But since we're removing some, it doesn't matter. It drops out. Okay, we're going to remove the arsenate. So basically, we're decreasing the product. So again, if you take it away, you're going to replace it. And then in this particular case, we're going to remove all. So we have to have some of the solid. It's a reactant, so it's going to shift back to the reactant side. Now, in this particular case, I have told you which way you could shift. But the other thing is if I were to ask, if I need this equilibrium shift to the reactant side, what could I do? Well, you could remove all of the As2O6, all of the carbon. You could increase the As4, increase the CO. Bottom line is you can be asked this either way. What happens when I add or remove something, or how could you make it shift? So keep that in mind as you work the problems. Okay, the next one is pressure must be maintained. So you must change the number of moles to keep the pressure constant. And remember, PV equals nRT. So what that means is that pressure is proportional to the moles. So if you increase the moles, you increase the pressure. You decrease the moles, you decrease the pressure. Okay? So that's one way. That's the overall pressure change. Now, how do you affect the pressure? If your reactants or products are gases, then you change the concentrations. Seen that one before. The other way is to change the volume. Remember, pressure is inversely proportional to volume. So if you increase the volume, drop the pressure. If you decrease the volume, you increase the pressure. So you're going to have to adjust the moles to keep the pressure constant. Okay, and I'll finish that out because there. All right, now you can change the pressure by the initiative of inert gas, neon, xenon, etc. But this will have no effect unless it is in the equilibrium. So you can add all of the neon you want. It'll increase the pressure, but it has no effect on the reaction unless neon happens to be in the equilibrium. So here we have pressure effects. And usually I ask somebody up or down. I'm going to go with down. So what we're going to do here on this one is we're going to decrease the pressure. All right. So in this case, we're going to decrease the pressure. So if we look over here, we only look at the gases. We have 6 moles on the reactant side, and we have 0 moles of gases on the product side. So if you have decreased the pressure, then on this one, we need to increase the pressure. Increase the pressure. So we're going to move to the side with more moles. Who has more moles? The reactant side, so we will shift to the reactant. Now, if I had said that we're going to increase the pressure, then we'd shift to the side with fewer moles because we want to lower it. Okay, so on this one, we have 1 mole over here and 2 mole over here. So again, if we're decreasing the pressure, we need to increase it, so we're going to move to the side with more moles again. Okay. So if we look at this one, we have 4 and 4, which means that as we decrease the pressure, you can't shift to replace it, so there's no effect because our moles are equivalent. It's not that there's not an equilibrium, and it's not that it's in the equation. Okay, now I'm going to switch colors because we're going to change on this one. So we said by decreasing the pressure. Let's say that we're going to decrease the volume. If we decrease the volume, the net effect is that we increase the pressure. So in this particular case, we would shift to the side, move to fewer moles. So your answers are actually opposite for the blue, except for this one. This one's still no effect because one of them's not better than the other. Okay, so this is strictly a teeter-totter. Who's shifting what way? Okay, the next effect is temperature. Well, temperature is actually really easy if you apply heat as either a reactant or a product. So if you think about it, exothermic reaction, heat is given off, so it's a product. In an endothermic reaction, heat is a reactant. So if you put it in as a reactant or product, so A plus B, A 2B, and it's an endothermic reaction, you'd put in heat or temperature. Or if it's exothermic, you'd put it over here. And then you just treat it as a reactant or product. It actually makes life a little bit easier. So again, in this particular case, I always ask somebody up or down. Well, I went down before. I think I went down before. So we're going to go up here. So we're going to increase the temperature. So in this particular case, if we look at this equation, this is an endothermic reaction. We know that because it's positive, so heat's going to go in as a reactant. So if we increase the temperature, that's the net effect of increasing a reactant. So we're going to shift to the product side. On the second one, it's an exothermic reaction. We know that because it's negative, so heat is a product. So if we increase the temperature, we're going to shift it to the reactant side. Now, decreasing the temperature is the net effect of removing heat. So it would have the opposite effect as we go through it. Now, if we put all of it together, we have a problem very similar to this one, where this is more similar to what is on the exam. And you will have an equation with a series of questions like this, and you'll be asked what to do. Okay, so if we look at it, and I'm going to go ahead and look at the equation. This is a negative, so heat is a product. And so we'll go. So we're going to add hydrogen. Now, what do we do with the constant temperature and volume? All you're doing there is making sure you're only looking at the hydrogen moving. So we're going to add hydrogen, which is a reactant. So we're going to have to get rid of it, move it to the product side. Temperature is increased, which means we're going to add temperature, which means you're adding a product. We need to get rid of it, so we're moving to the reactant side. If you double the volume, that means you increase the volume, which means you drop the pressure, which means you need to go back pressure-wise, which means you move to the side with more moles. So who has more moles? So we have 4 moles on this side, 2 moles on this side, so we're going to shift to the reactant side. We're going to remove ammonia. It's a product, so we're going to replace it. We're going to move nitrogen, which is a reactant, so we're going to replace it. We're going to add argon gas, which is not in the equilibrium. So if it's not in the equilibrium, there's no effect. And we're back to adding a catalyst. Well, what's a catalyst do? A catalyst speeds up the reaction. Well, remember, at equilibrium, the forward reaction and the reverse reaction are equal. And if we speeded both of them up, but they're both equal, we have done nothing. So there's no effect if we add a catalyst. If we weren't at equilibrium, then it would make us go to equilibrium faster, but it's not going to affect it. So you'll have a problem like this on the exam, or you may have one that says something to the effect of which of the following will make it shift to the product side, or which of the following will make it shift to the reactant side, and they'll add and remove different things. So you just have to look at each one individually. Then we have a closer to look, which is temperature changes and Le Chatelier's principle. So if you need a better explanation or a different explanation, look here. And then controlling nitric oxide emissions. This has to do with pollution in cars. So we're good to go on this one. And then this finishes the chapter. Now, this finishes this chapter, and then we are going to add in 17, which is the KSPs, and those will be added in, and you can look at those as well. They are simple KSPs, which means they're simple equilibriums, and they're just an application. So